For more than a century, astronomers have accepted a simple limitation. A telescope can only show you one small slice of the sky at a time, and only after long, patient hours pointed at a single target. That rule just broke. On a mountaintop in Chile, a machine has come online that doesn't study the universe piece by piece. It swallows the entire night sky whole, over and over again, and it has already found things that professional astronomers did not expect to see this soon. Its name is the Vera C. Rubin Observatory, and its first images, released to the public on June 23, 2025, didn't just impress scientists. They stunned them. This is the story of that telescope, how it was built, what it saw in its very first hours of operation, and why a single instrument on a Chilean peak is about to rewrite what we know about galaxies, asteroids, dark matter, and the structure of our own Milky Way. The Rubin Observatory sits atop Cerro Pachón, a peak roughly 2,700 meters high in the Coquimbo region of northern Chile, not far from the bone-dry expanse of the Atacama Desert. The location wasn't chosen by accident. Up there, the air is thin, dry, and remarkably still, and the desert below produces almost no cloud cover, no rainfall to speak of, and minimal light pollution. It's about as close as a ground-based telescope can get to the clarity of space itself. The idea for a telescope like this began life in the early 1990s as rough sketches for what researchers then called the dark matter telescope. By the early 2000s, the concept had matured into something far more ambitious, a wide-field survey instrument capable of photographing the entire visible sky again and again, cataloging everything from nearby asteroids to the faintest, most distant galaxies. Funding came together slowly over the following decade through the U.S. National Science Foundation, the Department of Energy, and private philanthropic support, and construction stretched on for years before the facility was finally ready. The observatory carries the name of Vera Rubin, the American astronomer whose work in the 1960s and 70s produced some of the strongest early evidence that galaxies are held together by far more mass than we can actually see. Studying the rotation of spiral galaxies with her collaborator Kent Ford, Rubin found that stars near the outer edges were orbiting just as fast as stars close to the core, a result that shouldn't have been possible if the only matter present was the matter we could observe directly. Something invisible had to be supplying the extra gravity. That invisible material became known as dark matter, and naming this observatory after her was a deliberate signal of its central mission: hunt for the parts of the universe that don't emit light. At the heart of the observatory is the Simone Survey Telescope, an 8.4-meter instrument with an unusual three-mirror design that lets it capture a huge patch of sky, more than 9 square degrees in a single exposure, without sacrificing sharpness at the edges of the frame. For comparison, that's an area many times larger than the full moon appears in our sky, captured all at once, corner to corner, in focus. Behind that mirror system sits the LSST camera, the largest digital camera ever constructed for astronomy. It's roughly the size of a small car, weighs close to 3 tons, and houses more than 200 individual sensors arranged with extraordinary precision, capable of recording nearly 3,200 megapixels per exposure. It photographs the sky across 6 different wavelength bands, from ultraviolet through the near-infrared, and a robotic filter-changing mechanism can swap between them in seconds. A single full-resolution image from this camera is so large that displaying it properly would require hundreds of ultra-high-definition television screens arranged side by side. That combination of light-gathering power and field of view gives Rubin an observational reach that no previous wide-field telescope has matched. It isn't built to stare deeply at one object for days. It's built to scan the whole sky, rapidly and repeatedly, and to notice the moment anything changes. When the observatory's first images were unveiled at a public event, the scale of what had been captured in just over 10 hours of preliminary test observations caught even seasoned researchers off guard. In that short window, not even the start of the real survey, just a systems check, the telescope had recorded roughly 10 million galaxies and Milky Way stars, along with more than 2,000 previously uncatalogued asteroids, 7 of which orbit close enough to Earth to be classified as near-Earth objects. To put that asteroid number in context, The entire global network of dedicated asteroid hunting telescopes typically finds around 20,000 new asteroids in a full year combined. Rubin matched a meaningful fraction of that annual total in a single overnight test run, almost as a side effect of simply checking that its systems worked. The centerpiece image from that first release was a mosaic stitched together from over 1,000 individual exposures, showing a portion of the southern Virgo cluster, the nearest large collection of galaxies to our own. Observers quickly nicknamed it the cosmic treasure chest, and it earned the name. Spiral galaxies drift across the frame at every angle. 3 separate galaxy collisions appear frozen mid-merge, their shapes visibly warped by gravity, and faint threads connecting galaxy groups hint at the larger cosmic web of dark matter and gas that stretches across the universe. Zoom in far enough, and the background dissolves into a haze of faint, reddish smudges, galaxies so distant that the expansion of the universe has stretched their light toward the red end of the spectrum. What made the moment genuinely staggering wasn't just the beauty of the image. It was the arithmetic. Astronomers noted that this single mosaic, packed with roughly 10 million galaxies, represents only about 0.05% of what the observatory expects to catalog over its full survey. Multiply that out, and Rubin is on pace to image something like 20 billion galaxies before its mission ends. A second flagship image showed the Trifid and Lagoon nebulae, glowing star-forming regions several thousand light-years away in the constellation Sagittarius, built from hundreds of exposures. What surprised researchers wasn't just the nebulae themselves, but everything packed in around them in the same frame: open star clusters, a dense globular cluster, and objects at wildly different distances and ages, from newborn stars still wrapped in gas to ancient stellar groupings, all rendered sharply in a single simultaneous capture. Within days, researchers were already reporting individual finds buried inside the test data: an unusually large, fast-spinning asteroid in the main belt, hints, in the shapes and brightness of distant galaxies, of supermassive black holes sitting inside galaxies that appeared far too young to have grown them. One scientist compared the discovery to finding a fully grown adult standing in a kindergarten classroom, something that, by the normal timeline of galaxy and black hole growth, shouldn't be there yet. What separates Rubin from almost every telescope that came before it isn't just size, it's rhythm. Most major observatories point at one target, gather data for hours or days, and move on. Rubin instead is designed to scan the entire visible southern sky roughly every 3 to 4 nights, taking around 1,000 exposures a night, each lasting about half a minute before the telescope repositions and fires again. That nightly haul amounts to roughly 20 terabytes of raw data, sent via a dedicated high-speed fiber link from Chile to a processing facility in California, where automated software calibrates each image, corrects for atmospheric blur, and, critically, compares every new frame against everything captured before at that same patch of sky. Anything that has changed since the last pass, a star that brightened, an object that moved, something that appeared where nothing was before, gets flagged, and an alert goes out to the global scientific community within about a minute. This is the feature astronomers describe as turning still photography into cinema. A supernova that once might not have been noticed until it was already fading can now be caught the moment it ignites. A pulsating variable star, an asteroid on an odd trajectory, a faint object crossing the solar system on a path no local body should follow. All of it becomes visible almost as it happens, rather than being discovered after the fact. Over its planned 10-year run, this mission, formally called the Legacy Survey of Space and Time, is expected to catalog somewhere around 40 billion individual stars, galaxies, and other objects, generating hundreds of petabytes of data in total. Officials overseeing the project have pointed out that the data gathered in just its first year is expected to exceed everything collected by every other optical observatory in history, combined. Beneath the sheer scale of what Rubin detects lies its deeper purpose, confronting the two biggest blank spots in modern physics: dark matter and dark energy. Together, these unseen components are thought to make up roughly 95% of everything in the universe, while the ordinary matter that forms stars, planets, and everything we can touch accounts for only a small fraction of the rest. Rubin can't photograph dark matter directly, nothing can, since it emits no light. But by mapping the positions and shapes of billions of galaxies with extreme precision and measuring the subtle way that unseen mass bends and distorts the light of galaxies behind it, a process called gravitational lensing, researchers can build the most detailed map yet of where dark matter is concentrated across the observable universe. For dark energy, the mysterious force apparently accelerating the universe's expansion, the strategy involves tracking millions of a specific type of exploding star, whose brightness is predictable enough to serve as reliable cosmic measuring sticks, alongside long-term changes in how galaxy clusters are distributed across space and time. The central question researchers hope to answer is whether dark energy behaves as a true constant, as Einstein's equations originally suggested, or whether its strength has shifted over cosmic history. The answer, whichever way it lands, would reshape core assumptions in physics. Rubin's reach extends much closer to home as well. From our position inside the Milky Way, roughly 26,000 light-years from its center, mapping our own galaxy's outer structure has always been difficult. The faint, sparse stars scattered through the galactic halo are hard to detect with older instruments. Rubin's combination of depth and wide field of view makes it uniquely capable of finding them. A key tool for this work is a class of pulsating stars whose brightness rises and falls in cycles lasting several hours in a pattern directly tied to how intrinsically luminous they are. That predictability lets astronomers calculate precise distances to these stars even when they sit tens of thousands of light-years away, far out in the galaxy's diffuse outer halo. In its earliest test images alone, researchers already picked out dozens of these stars in that remote region, and the finished survey is expected to catalog around 100,000 of them. What this ultimately reveals is the Milky Way's violent history. Many of the stars scattered through the outer halo weren't born there. They were torn loose from smaller dwarf galaxies that our galaxy consumed over billions of years, leaving behind faint streams and loops that still trace their original orbits. The most famous of these, associated with the Sagittarius dwarf galaxy, has been studied before, but Rubin is expected to uncover fainter, previously unknown streams and structural quirks in the halo, some of which may point to encounters with clumps of dark matter itself. In effect, the survey is expected to reconstruct a kind of geological record of our galaxy's mergers, written in the faint scattering of ancient stars. Perhaps the most quietly radical part of the Rubin project is what happens to all this data once it's collected. It doesn't stay locked away. The observatory has built a public viewing platform that lets anyone browse the full-resolution imagery directly through a web browser, zooming from panoramas containing millions of galaxies down to individual stars. Because the flood of nightly data is simply too vast for professional teams to comb through alone, the project has explicitly welcomed amateur and citizen scientists into the search, expecting that some genuine discoveries, an unusual comet, an anomalous flare, an object nobody has flagged yet, will first be spotted by someone scrolling through the public archive rather than by a research team. Alerts about changes detected each night are distributed openly to registered users everywhere, without any priority queue favoring major institutions over smaller observatories or universities anywhere in the world. There's one more category of object Rubin is uniquely positioned to catch, and it may be the most tantalizing of all, material that doesn't belong to our solar system at all. Twice in recent memory, astronomers have spotted objects passing through our solar system on trajectories that no comet or asteroid born here could follow, visitors from other star systems entirely. The first, a strange, elongated body discovered in 2017, was already on its way back out into interstellar space by the time it was found, and its odd shape and unexplained acceleration are still debated. A second, more conventional icy visitor turned up in 2019, trailing a comet-like tail. In both cases, researchers had only a matter of weeks to study the objects before they faded from view, and both were already past their closest approach to the sun by the time anyone noticed them. Rubin's advantage here comes down to its scanning rhythm. Because it revisits the same patches of sky every few nights rather than waiting for a chance sighting, an incoming interstellar object is far more likely to be flagged early in its journey through the solar system, potentially giving scientists months of observing time instead of weeks. Researchers estimate the survey could turn up dozens of these objects over its 10-year run. Each one would carry a chemical fingerprint formed around a different star entirely, a small, physical sample of a solar system none of us will ever visit. What Rubin captured in its opening hours was never meant to be the finished story. It was a proof of concept, a warm-up run before the real 10-year survey even began. And yet those first frames already contained collisions between galaxies caught mid-motion, thousands of previously unknown asteroids, hints of black holes that grew impossibly fast, and stars scattered across our galaxy's remote outer edge that trace collisions from billions of years ago. The universe captured in those images was always this busy, this layered, and this much in motion. What changed is that, for the first time, an instrument exists that is wide enough, fast enough, and sharp enough to catch nearly all of it happening at once. Not a single photograph of the cosmos, but the opening scene of a decade-long film. And by every indication from its very first night, that film is going to be extraordinary.